Okay. Just give me a second. Okay, so before that, I used to work for Pivotal, actually Pivotal Labs here in Berlin, and sometimes I also work for Accenture Digital. So this is my team. So without them, we are a small team, and actually without them, with these projects and all the stuff that I'm talking today, would not be here. So it's really always good to show them again. This is Idealo Tech. I work for Idealo, and we also do a lot of open source. So if you want to know what we do, you can read, for example, on our Idealo Tech blog. But also, if you would like to see what kind of open source contribution we do, just check out our Idealo account. Also, for the project that we are doing, we do open source a lot of the stuff. So I will also do some pointers today. Yeah, let's come to the use case. So this is like a small subset of use cases that we do, but I still like to show them because they have like kind of great value. The first thing that I want to show you is from our hotel price comparison. So who actually of you knows that Idealo actually has a hotel price comparison? Okay, not everyone, but no, you know. So as I said, Idealo has a price comparison. In Idealo, we have like around 2 million accommodation listed. Out of this 2 million accommodation, they provide us with 300 million images. And if you would divide all the accommodations by the hotel images, you would have something like 133 images per accommodation. And every day we get like 1 million images every day. So it's a lot of images if you think about this. If you go on our website, though, if we think about another dimension, photography is very important, right? So photography is one of the most important thing when it comes to booking a hotel or accommodation in general, right? So, for example, if you think about your own experience, let's say you go on a travel, right? You go on Airbnb or you go on Us or any other stuff like TripAdvisor, right? One of the things that you're probably also looking at is at the photo, right? Because it's important to get a good feeling of how it looks like when you're there. The problem, though, is when you go on our website, let's say this example here, you see this kind of listings, right? So if we look closer of one of the listings, it doesn't really look nice, right? So, I mean, what the fuck, why do you have like a woman in a sauna, right, as a first listing? So it is not really kind of welcoming if you think about this, right? And if we dig further into the gallery, so if we go into this listing, you can see like also more pictures, right? Like every hotel user provider platform would also provide this. And if we have a look at this closer, we can see, for example, there are like a lot of bedrooms in there, right? But then the problem with bedrooms is they have different positions, right? So, for example, if you look at position 19, is a bedroom that is more like visually more better, right? If you compare that to position 1. Similar to reception. So if you think about position 3, right? So I don't think, from my perspective, position 3, so this image is not really nice. If you think about position 17, it is still not very nice, but compared to position 3, it is much better. So one observation that we have to do is beautiful images should actually appear earlier in the gallery. Then if we look at another example here, what do you think is the most common denominator of this gallery? Anyone has a clue? You can scream into the room. Huh? 9? No, what is the common denominator of this gallery? So what is how do they look similar to each other? Beds, yeah. So there's a lot of bedrooms, right? So if you have a gallery like this, it's not very informative, right? So it's like, you go into gallery and you show, out of 20 images, you show 15 images bedrooms, right? So you want to see more stuff. You want to see the reception. You want to see the gym, right? You want to see the view of exterior. So to get an informative experience of the hotel that you want to go to, right? So another observation is you want to ensure that different areas get also depicted. If we think about the optimal gallery, it would be something like this, right? So you have bedrooms, you have bathrooms, you have a restaurant, you have a facade, you have a fitness studio, and you have a kitchen, right? And within each of the category, you basically have like an order of images, right? The order is determined by how beautiful they are, right? So how visually they are in, compared to other images. And if we drill down the problems, actually it's a two-part problem. So the first part is you basically take the hotel images according to the hotel property area, and the second is you want to predict the aesthetic, right? So aesthetic in terms of beauty. We actually solved both of the problem, but today I just want to present you the second part because I think the first part is very simple. We have very simple solution for this already, and the second part is more difficult because trying to teach a computer to understand beauty is something not very easy because it's also very difficult for us, right? And of course, we are using deep learning for this. Why? Because it's state of the art. So in terms of deep learning, what we use is kind of a technique. It's called transfer learning. So a lot of people probably might heard of it, right? In transfer learning, you basically train a model somewhere else before, right? From another task. For example, let's say you want to classify this is a cat versus dogs, right? And then basically you take the weights and then you replace like kind of the last layer, like the last neurons information that you need basically to train something else on another task. This is called transfer learning. In our case, we use a pre-trained convolutional neural networks on ImageNet. ImageNet is a data set provided by a research institute a long time ago, and there was a competition around it. And basically, they trained several models on this. For example, MobileNet and VG16. In terms of training, so of course for deep learning, it's not feasible, to train it on your CPU. So for training, you need a lot of graphic cards. And basically, what we do is we are using AWS to do this. And this is basically our setup. So for the setup, we using our Docker file, we pushing it to ECR, which is kind of an equivalent of Docker Hub. And then we have our custom AMI, which we created, where we place our data set in there because our data set is actually quite huge. So it's like 20 gigabyte, right? So every time you want to retrain, you don't want to kind of push it up again. And from there, we are using Docker machine to spin up EC2 instance with a GPU graphic cards in there, right? And then we basically, after training, we copy it to S3, and then we store the model again. And for the evaluation, it's kind of a similar setup to training. So we're also using Docker machine to spin up the cluster, and then also we're also using Jupyter Notebook basically to visualize this. Actually, this training workflow is kind of outdated already because we are using Terraform these days to simplify and automate a lot of training steps. But yeah, it's still very valuable, and actually we also have it on our GitHub account if you want to look at this and use it to train your own models. It's very simple. Okay, let's recap the problem again. So if you think about the listing here on our website, so the problem is very simple, right? You have a listing, you have a first image, and out of the first image, you have a gallery, right? A gallery contains a set of images. And out of this set of images, you want to determine what is actually the most pleasing image. In this case, we would say this is the best image and not the other first image. So how do we solve it? So we solve it via, as I said, deep learning. And for this, we basically followed a Google paper, which is called NIMA, Neural Image Assessment. And basically, we trained two models. One is the aesthetic model, and the second one is a technical model. If you think about quality of images, right, there's always two dimensions that you need to think of, right? So one dimension is of course, aesthetic. So what is the angle of this room, maybe? How is the composition of these rooms? Are there many humans in there or less humans? And then you have things like technical quality, right? Technical quality is for example, hey, is there any distortion, right? Or is your image blurred, or any resizing happening where you have some loss of information, right? My focus is today only on the aesthetic because, yeah, we don't have much time. So I will go through two iterations that we've done for the project. So the first iteration is where we train on a public data set. So it's an open source data set provided by a photo community. It's called an AVA data set. It is 20 gigabytes big, so it's quite large. And it took us 8 weeks to do this. And then afterwards, we had another iteration where we were fine-tuning our model because we put the first model into production and it didn't really work well as of this time. But I want to show you why it was the case. Okay, so one of the characteristics of the neural image assessment model is that they are not using standard loss functions like cross entropy. So cross entropy is, when you have kind of experience in deep learning, it is actually the standard loss function to do image classification. But for us, if you think about aesthetic, right? It's like a ranking problem, right? It is very subjective. So for example, let's say my colleague look at a picture, right? Let's say this room, he would give this room maybe a 6, right? I would say I would give this room a 4 because I don't like dark rooms, for example, And if you think about this kind of problem to model this mathematically, it is not very trivial, right? Because you're looking at distribution. And the good thing with the neural image assessment model, it takes a distribution into account. And here we are using alpha-mover distance instead of a cross-entropy function. And in this case, this is the results of the first model that we trained on the public data set. And then we predicted it on a data set that we created ourselves as a holdout data set on our hotels. As you can see, we have expected means from 1 to 9. So we have like 200 images where we say, hey, these images range between 1 and 9. And the model that we use as a first iteration basically only could capture like ratings between 3 and 6. If you look at the standard deviation, because we have a distribution, we can also look at the standard deviation. We can also see that the first model doesn't really capture the inheritance of the ratings, right? And that's actually valid because if you think about what I said, we trained it on a public data set, right? That is, that can be anything, right? That can be ratings from a room, that can be ratings from a landscape, that can be also ratings from food, right? So it doesn't, capture our data at all. Nevertheless, we put it in production because we wanted to see how does it actually perform for our model, for our data set, right? So if we look at the example that I showed at the beginning again, so it is not a handpick example. So everything that we did is, like random sampling. So we don't, pick the best picture and the worst picture. It's everything is, like random. If you see it here, actually it did a quite good job. So the first picture is quite nice compared to picture 12, rank 12, something like this, right? One thing where the problem is the ranking, right? As you can see, the best picture has 5.2, 5.3, almost 5.3, and the last picture has only 4.5, right? So you can see that the discrepancy between the first picture and the last image is not very high. And this is problematic because, if you have a logic system still in your application, you say, hey, I only show pictures that are over 7. This, for example, would be not possible. Here's another example. So I think the first image is horrible. It is really not the best, but also our model also didn't really predict the best model, right? I would also not really like to show a toilet as a first image. So that's why what we did again, we had to rethink our problem, right? And we identified that the first results are not good because we needed more domain-specific data, right? And also because we deployed it, we also recognized that hey, using VGG16 is not really feasible for us because if you know a little bit about these kind of models, they have like 100 million parameters to optimize. So it's a lot of computing power necessary to do this. So we decided to rather to go mobile net where the network is just smaller, right? And because as I said in the beginning, we have more than 300 million images, and we have every day 1 million images coming in, right? So you cannot just cope with the amount of data that we have when we use VGG16. So in the second iteration, what we did basically, we recognized, hey, we need to do something. We need to integrate domain-specific data because this way, we can improve our model. And what we did is, we built a simple labeling application to model some of the data, and then 12 people from idealo Reise and our data science team labeled these images. So we labeled 1,000 hotel images and 3,000 hotel images for the technical quality. Then we fine-tuned the aesthetic model on 800 training data, and also then we built the holdout data set that I told you before with 200 images to evaluate our model, right? Because in machine learning, the case is you're building a model, right? And you want to see how well does it generalize to all of the data, right? So you cannot build a model on 3 million data, or 1 million data, or 2 million, or 3 million of data, right? So you just take a sample that makes sense, right? Then you split it, for example, here in train and test, right? You train it, and then you test it and see, hey, the testing should kind of represent the entire data set. Yeah, so as you can see, this is a result of our second iteration. As you can see, the distribution looks quite nice. So our next model with our domain-specific data is able to capture the ratings between 1 and 9, and also the distribution is also well captured. If we look at some examples again, I think the first model did already quite good job. The second model did even a better job because it's still the first picture that he depicted on the first iteration, but now, as you can see, the ratings, it makes more sense, right? So it's a 7.6 versus a 4.3. So you just have much more of discriminatory power in the model now, and which is very good because in a production system, you need this kind of threshold as well, right? And then if we look at this example, I don't know if you agree with me, I think the first image now will be much nicer compared to the guy in the reception. All right, after this, we were pretty happy with this, with the model, and then we deployed our model on OpenShift, so it's on our own Kubernetes cluster. At one point of time, we actually had 100 pods, so containers running for 2 weeks, because, you know, going through 300 million images is not very easy, especially when it comes to machine learning. But we did it, and to date we've scored like over 300 million images now. And of course, you know, when you think about our whole training, testing, and whatever, right? It is kind of, you know, like a experiments, right? But what happens when you put it in production, right? So what will the model do? Because you never know, because you hope that the model will generalize well on all the images. What we did now is we wanted to test on 1 million scores whether our model is really doing well or whether, you know, we don't know what it did, right? And if actually we plot the distribution of 1 million scores, and you can see it is capturing between 1 and 9, right? So it means it is doing something that we expected, because there are images that are just a 1, and there are images that are 5, 6, and a 9, right? So if the model would only do 5 and 6, we would be very worried about this, because we don't know, like, okay, what is the model doing? And of course, we took a random sampling of images. So let's say if we have some low scores here, you can see, yeah, the model is doing quite well, right? If you look at the images, it is the landscape is not really good looking. The laptop, also the toilet. If we look at middle scores, I think compared to the low scores, relatively, right, it also looks much better versus the low scores. If you look at the bedroom and the left upmost front, right, also the landscape as well. But one thing, of course, you know, there's also this spaghetti whatever thing here. It got a very high score, but this is true because it inherited a lot of from our previous models, right? So that we pre-trained. So, and we didn't, you know, in our data set controlled for food. So, but it's still quite good for us. So it was not problematic. And if we think about high scores, it's doing a quite nice job, right? So if you think about the high scores now, I think the gallery looks really nice. So if you really, you know, can filter out, like, you know, just show me the images which are higher than 5 or higher than 6 and 7, you know, you get a very nice, good-looking gallery. So, yeah, so this was the first use case. The second use case is about automatic product gallery generation. It's a very interesting. So if you go on idealo and you know we are a price comparison website, right? You, for example, are looking for products, right? And let's say in this case you're looking for a helmet, right? And when you go into the helmet, you see this pinky helmet here, and you see like the price tag, the name, the price chart, right? You can also subscribe to our price alert as well. But then you can also see we have a gallery, right? So if you're looking, go into the product or like at every other e-commerce company, you want to see how does the product look like, right? So you want to have the feel of the real user experience when you go in a shop, right? And so for us, we know that if we have more images, our conversion will also be higher, right? So this is true because if you get a feel, you are also more likely to buy this kind of things. The problem though is creating this image gallery for each product is very cumbersome. So this is a video here. I want to show you. We have this internal tool which is called Media Manager, and basically we have content people around 180 something. They have this helmet here, right? They're looking for a specific type of helmet, and basically what they do is, hey, okay, there's this Abo small pink helmet, and then okay, suggest me some images, and out of these images, the content manager has to reorder, and then delete images that he doesn't really like, right? So if you think about this, for one image, I mean, it's pretty fine. I mean, everyone can do one image, right? But if you think about that, we have 330 million product offers every day, mapping to a lot of millions of products. It is very cumbersome, right? So you cannot just do it every day manually all the time. And this step, for one product takes around 50 seconds. So it's quite cumbersome. So optimally, you would have something like this. So like for especially in this case for helmet, because we started with helmet first as an MVP, hey, go into your system and then press one button and please suggest me the optimal gallery based on a model, right? And give me this gallery so that you have a left profile view, a left view, right view, and a rear view, right? And from a machine learning use case, it's very simple. So you have some training data, you train it, you get a model, you have a new classifier, you get some new data in, so all the images that you get from the helmets, right? And then give me a prediction and create this optimal gallery. Then, of course, the first thing that we do is training data doesn't come for free. So we, of course, at the first beginning, we needed to label the data, right? So we had things like, we built also an application that we took actually from our other projects. We built an application and basically collected training data with our content team. We started basically with 100 labeled data because, labeling data is not very trivial, right? So if we just go back to this example again, if you look, for example, at the rear and the front, you can see if I would not show you the other thing and the labels, it would be very difficult, especially for us, right? Because to understand what is actually the front and what is the rear, because I don't have the domain expertise for this, right? So we started basically with this 100 images to get a feeling, hey, does this classes make sense, or do we need to change that, right? And then afterwards, we did another iteration. We increased it to 1,000 images. We labeled it again with the content team, with us as well, and then basically retrained it. But then we recognized, okay, the model is still not doing well, right? Because there are still some class imbalances that we had to take care of. For example, there was not a lot of shutter in the image gallery, right? And then we had to continue. And then afterwards, we collected 10,000 image data, and then we labeled it, and that was enough then. So a lot of people actually tend to ask me all this time, how much data do you actually need to train your machine learning models? And my answer is always, I don't know, because there's no formula at the end of the day that tells you, hey, take X times blah, 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 and then you get the optimal data. This is something that you can only do via experiments and via iterations. So afterwards, we put it in production. So I just show you the final results. Same thing, the content guy is looking for helmet. Then let's just wait a little bit because our system is slow in terms of loading. Okay, let's look at the helmet, right? And then basically there's only one button. So label canon is the machine learning space, and then the automatic suggestion. So as you can see, So the gallery already suggested like the perfect optimal order, and also basically removed all of this stuff. So this is perfect. We of course tested our application. So with our new approach, we actually shortened the time for our content people to work on this by 75%. So before that, it took them like 50 seconds on average. Now it takes them only on 11 seconds on average, and 11 seconds is actually including with the loading as well. So it's not about like that he needs to do something. As a side effect, the cool thing with this is the classifier works well now with 5 other helmet categories. So it's not only the categories that we did, right? And yeah, so in the future, we are gonna want to roll out to other categories like smartphones, I don't know, computers as well. So we are continuing to work on this. At the end of the day, we have 2,000 categories. So it's a lot of categories that we need to work on. And basically, yeah. Okay. So the last use case that I want to go very quickly with you guys is it's called low to high resolution image. So if you go into our website again, right, and then you're looking for a product, let's say in this case it's a coffee, right, and let's say you are on a mobile phone or anywhere else, right, or you are, for example, you're like my mother and the mobile phone, and she's very old and she cannot really see well anymore, right? So actually she has like a 2 or 4 point zoom on her iPhone in this case of today. And what we want to do is, you want to give a user a good user experience on this as well. For example, if you zoom in, right? So this is the expectation. So you zoom in and you get a very large image as well, right? And if we think about this, this is actually our reality. So not every e-commerce shop provide us with high quality data, right? So you think about yesterday, there was a talk by Mr. Specs where he actually had a lot of high quality data, and his problem was more like compression, right? So reducing the images to serve it well in terms of speed. Our problem is different from the angle that we sometimes don't get high quality data, but we get very low quality data, and we still want to give a good user experience to the customer. And the problem statement, as I said, is very simple. So you have a low resolution image and you want to take a deep learning model, in this case a convolutional network, to upscale the images, right? So that you can show it to the customer as well. In this case, it's pretty simple. We use, as a first beginning, residual dense neural network architecture to build our model. And the setting is like this. So we are using Keras and TensorFlow to train our model. We trained it basically as a first iteration on a public data set called diff2k. And then basically we train it for an entire day and then monitored if our model converge. Luckily, our model converged. And basically, here's an example how it looks like. So for example, this is a image of a basket, right? On the left side, you have the high resolution image. On the middle side, you have the linear scaling, the baseline model. And then on the right side, you have a super resolution model. So you can see, I think it's very, I'm not sure if you can see it, but if you compare the super resolution to the linear scaled model, it is better because it's more crispy, right? Because in the baseline model, you basically take a pixel-wise and then just add it up as a nearby color-wise pixel, right? And of course, we wanted to not test it only on landscape, but we want to test it on our product, right? If you think about this year, the Birkenstock Sandal, I think it's too far for you guys, but if you look closer, you can see the model is still not doing a good job, right? Our first iteration. But this is true because our model was trained on a public data set which has landscape and not product data. And then you can see the model still has a lot of noise around the Sandal. There's a lot of fractures not a lot of detail still that we want to show. If we look at the the iPhone, you can see the difference more clear. So if you look at the Apple symbol, at the iPhone text, also at the camera, right? There's a lot of pixels as well. So it's not really perfect. Of course, we knew about this, and what we did next basically is we wanted to see how would the model improve if we train it on our data, right? Because the model is only as good as the data as you feed in. And then of course we also recognize another problem. We know that a lot of our e-commerce shops, they don't only send us like very small images of this, but also very noisy data. Even the high quality data that we are training is very noisy, right? So it is not like BMP, it's JPEG already, it is resized, right? So basically we wanted to incorporate some denoising because we want to have the model learned how to handle denoising as well. So this is our catalog data, right? So we have a lot of images, as I said, ranging from shoes to whatever. And then basically, this is the denoising step. Basically, we took an image, put a 50% compression or other levels there, and then feed it to the model so that he hopefully reconstruct the image without the noise. If we, for example, look at the iPhone again, right? So the first one was only the diff2k data set. The second one was the diff2k plus the idealo data set. And then the third and fourth one was with compression. As you can see, like from left to the right ones does a better job, right? But you can see that when you put a lot of compression in there, that the model learns to smoothen out everything, right? It smooths out the Apple symbol, it smooths out the Apple text and all the text below that, but also the camera. So we needed to kind of a trade-off to preserve these images. And if we look at another example here as well from the Birkenstock Sandal, you can see, hey, the model with the idealo data and with the compression is doing actually quite a good job. For example, if you only look at the lace, right, compared to the diff2k data only and the cubic interpolation. If we look at other areas though, for example here, this is still doing a good job. So it's smoothed out this area around the Sandal as well. And but if we look closer, like here, I think our model is like with the compression and the idealo data is not doing a good job because it didn't preserve the details, right? So basically, what we needed to same thing for the text, right? So it is actually comparable quite well, but it is not as crispy as if you think about the diff2k data without any compression. So what we did next was basically, so it's not on the slide, but we're using GANs, so generative adversarial networks, to basically trade off the details and the smoothness of the images. It's actually open source, so if you like to get to know more about this, it's on our idealo GitHub page. But also, if you would like to read more about the details, how we do things, we just released it 1 week ago, how we for our next iteration of this project. So we also wrote a blog post about this. Yeah, so this was a subsample of our projects. Of course, it's not the only projects that we do. There are other things that we do. So as I said, we're also tagging hotel images. We are tagging products. We're doing recommendation engines. We did a project with sales prediction, price alert automation, and also product matching. So there's a wide range of products that we do. This is our main research focus for my team. So we really like to understand what the machine learning model is doing, especially deep learning, because everyone believes that deep learning is a black box model, but there's a lot of research into these areas now to understand deep learning models, and it is possible. Then we want to understand how to efficiently deploy our machine learning models, because we have a lot of data, right? And when you think about training on 1,000, 10,000, 100,000 of data points, it is very simple. But if you think about millions of data, it is not simple anymore, right? Then another area that we are also interested in is auto machine learning. So we believe, I believe that the job of a data scientist or a machine learner engineers would change a lot in the next 2 to 5 years, right? So there's a lot of problems solved. So it means that you will get a lot of optimization problems solved automatically. And basically, this is actually an area where we're going, because if you have enough computing power, you can solve the model easily via an optimization problem. Then, of course, another area that is very important for us is the data collection process. So a lot of people, tend to forget it because they just, hire a data scientist and they believe, hey, we already have the best data in the world. You just here, you just need to use our gold, right, and kind of like make use of it, but it's always not true. So a lot of companies, especially also ours, we needed to collect a lot of data, and we need to do label data, right? We need to provide generated data, and this is very important for us as well. Yeah, so thanks for your attention, and hopefully there's some questions. There's one question.
Hi Dan, this is Dan too. Thanks for the good talk. My question is, perhaps I missed it, how long did it take to train the models?
Which model?
The first one you presented.
That took 4 or 5 hours.
4 or 5 hours. And how often do you repeat this process? Do you keep this trained model, or do you...
For this thing, we actually keep this model because if you think about hotel images, right, in terms of the visual aspect and so on, it doesn't change that much, right? Okay. So you only will retrain a lot if you think that you get a lot of new data coming in and the change is so dramatic. Okay, and may I ask another question? Okay, how often or do you think about repeating the training process for every category automatically? So yeah, so in the media manager, the good thing is I would say it's very disturbing, but we have a lot of monkeys in a way. So the content people, in the media manager, they're already doing it in a way, right? So what we want to do is we want to integrate in the media manager, and if a new product comes in, they have to do it anyways, right? And basically, you basically type it in and then get the new label, right? And then at some day or at some trigger, they should do the retraining.
Okay, thank you.
Hi, thanks for the talk. Quick question with the media manager and kind of getting the images in order, and you had like mechanical Turks, I guess, people label it and ordering it. Why didn't you use like the reordering of the content team as input for how you want to order it in the first place?
Well, this is always a good question, but as I said before, this is always not collected, right? So if we would all have this data already, then we would not have to label all these things, right? So it's just because they didn't think about this, right? A lot of problems occur because they don't know how to collect the data basic for the machine learning model, right? And this is one of the cases.
Hey Dad, thanks for this very interesting talk. I would like to know about this classification of these pictures, like how nice do they look? Did you try, because you said you think about understanding, deep learning, did you try to find out why the model classified the rank as it did? Like what it looked in the picture, yep. What the reasons are for classifying a 7 instead of a 4.
Yeah, so of course we did, but it is a little bit more non-trivial. I think I can show you this a little bit. I think we still have 6 minutes. So we basically. It's just an approximation, because so we are using Lucid. Lucid is doing some neurons activation in a way, right, to understand the neurons of what it is. So my team literally just gave a talk recently, and we have some Colab notebooks onto this. So if we go through the visualization techniques, I can show you a little bit what we did. So basically. Just give me a second. So basically, it does some kind of activation to understand, for example, what is a neuron thinking, right? In this case, for example, hey, we see, is a neuron basically a jellyfish? Is it a balloon, right? So, or anything else. And we also did this for our ratings. So for example, if you look at a aesthetic score of 0, I don't know if you can see it, it is very plain, right? So there's not a lot of structure in a way, right? And if you go further, like 1, 2, 3, whatever, 4, 5, 6, 7 on, you know, you have more details coming in, you know, you have like also eyes, right, or some shapes. Of course, this is very abstract, but it only gives us an indication what is actually the neural network looking at, right? So it's very still, you know, I would lie if I say, yeah, because of this, I understand it completely, right? But it's just an indication.
Yeah. Yeah, thanks.
Okay, I think that's it.